The first question would be one second. B is this. A is 3 by 2. So yeah. So what is a projection matrix? This is problem 3. What is a projection matrix? Rasubra, do you know what is a projection matrix?
You have to see.
Right. So
Like,
will it be
no,
B
not
square
see.
equal to B?
Yeah, so it's item, but it's property, like not the definition.
No. So is that? Oh, that's a property.
Yeah.
Right. So what is
So
this
it's idempotent. It has to be idempotent and linear.
and linear?
Yes, something like that.
But
I
matrix.
have to see.
Just check it. Because projection matrix, I don't know what should the definition be. There can be many definitions. That is the problem. Essentially. Yeah, I could make a definition, but let's see what the official definition is. My laptop just shut down.
It will also vary according to the different books, right?
Yes, that's why I'm not saying a definition. I have a definition which, that, okay, when you conjugate it, then it will look like identity in one corner and zero everywhere else. So there is a P such that when you do this, but this will sound completely meaningless, right, to some of, if you don't know what I'm trying to say. This is my definition. And this also implies this property very interestingly, but I'm not
the
going to.
definition is given as that let S be a subspace of f to the power n.
Okay, SB. Okay, so we'll write the definition.
And
S is in R to the power n. Okay.
And it is a subspace.
Subspace. Yeah, that's important.
And T is a complement of S.
P.
T is the complement of S.
Okay, so T complement meaning like this.
No, like S plus, yeah.
Okay.
Equals to R to the
S plus T.
S direction T equals to R to the power.
Okay, so this also you should explain what this means. Like, what does this mean?
This means that every vector in R to the power n can be written as like uniquely written as one vector from S and one vector from T.
Okay, uniquely. Interesting.
Uniquely.
Can you give an example?
1001 and R square.
1 0 like this.
Like span of 10.
Yes,
Span
span of 1 0, right? Span this line and this line, and
Yeah.
you get R square. But this is not a good example. This is just saying basis. As any vector can be uniquely written using this and this. Yeah, from one vector from this and one vector from this. That is basically the same thing as that. This is the basic. Can you give some other example? Some more interesting.
R cube.
R cube, maybe. Okay. How?
A span of 1, 0, 1, 0, 0.
Okay. Like that only you will give.
Okay, sorry.
No, I'm not saying. I'm just asking.
No, my example is 0. Okay, so another example can be set of all polynomials.
Now you're giving interesting examples. Okay, so that we can feel this a little bit more in a different, from a different angle. Okay, so P is all polynomials. Okay,
And one is set of all even polynomials and other is set of all odd polynomials.
Okay, so E and O are understood. I'm not writing. E and O are in. A set of all polynomials form a vector space. Okay, set of all even polynomials form a vector space. Adish, is that okay?
Yes.
Yeah, because even polynomials actually, as you would know, comes down to all powers are even. Only the even power
I
terms,
know.
and so they form a vector spaces. Okay, then Rasubra, what's the next thing?
So E directs some O equals to P. So every
Ah,
polynomial.
yes,
Hmm.
right. You see, Adish, this is the interesting example. Right? Every polynomial can be uniquely, and you know that it can be uniquely written using the odd powers and the even powers. Yeah, using one polynomial which only has odd powers, one polynomial which only has even powers. It's a very natural way to write it. Good. This is an example, nice example. Okay, so it helps you to break your vector space, and nice. So you, a good example. Okay, so I'm erasing this. Okay, then what's next?
Then a matrix A n cross n is said to be a projector.
M cross n or n cross n.
N cross n. N cross
Okay.
n
A n
is said
cross. Sorry.
n is said to be a projector
Or projection
into
matrix.
S.
Oh, sorry. Is said to be a projector
Projector into S
into S
along T
along T. Wow, this is some nice. Seems like some serious maths. Yeah,
if
along T.
for all x belongs to f to the power n.
If for all x belongs to, okay,
F to the power n. Ax is projection of x into S.
Ax is projection. Ax is projection
Of x into S
into or onto same thing S
along T.
along T. Now you have to tell us more things. What does this mean?
Okay, so it's fine. Like I read it, but I forgot.
Okay, yeah. So maybe this one, I think if I understand it, then I will say. Then you can check me. Yeah.
Yeah.
So yeah, x basically x is in Rn. Okay. So this x will be S plus T. Right. And
Yeah.
this Ax, what should it be? S. That's what it should mean, right? The shadow of x on S.
Yeah.
Okay. And but then along T, where my definition is sort of missing that along T. Wait, projected into S along T. This one is a little unclear to me. I mean, what I would say is then that if there is any vector T, then T goes to 0. Right? And if any vector is in S, all of those actually follow from the first one, if you see.
Yeah.
Right? So vectors that are in S, it doesn't change them. Vectors that are in T, it sends them to 0. And vectors, yeah, just splits and returns the S part. This is what I feel is the definition.
Yeah.
Wow. Into S along T. Yeah, this should be like perpendicular to T, but anyways, okay. Yeah, maybe the direction of the. Okay, but then give us example of such a matrix so that we can understand what is this more.
I don't think any example is given. Let's see.
Okay, then I will give an example. Okay,
Yeah.
so yeah, so if no example is given, then 1 minute. Okay, I'll just give some example. It's a 1, 2, 3, 4, 0, 0. Okay, let's look at this matrix. Okay.
Yeah.
So can you now predict the S and T? Or predict some S and some T?
Just keep the diagonal elements in one and 2, 3, like the other 2 elements in the other.
Like, can you say, so okay, can you say then what is S? Span of what, or what to say?
Oh, that's the matrix.
Yes, that's some. So I'm saying that is A. If this is my A, and I am claiming that this is sort of a projector, a projection matrix. It's a projector. Then what is S and what is T? What should be S and what should be T? So you can look at these properties, right? What is it that it is fixing, and from here, if there is something, if it is a projector, if it's not, then it's wrong. It's probably wrong, right? Doesn't seem to, I mean, it, just a minute. I mean, there are some trivial examples, but don't want to give trivial examples. Yeah, okay, I'll just give trivial example only. Let us see, because I'm not able to think of a good example. This. So now can you say what is S and what is T? Right. So you see, S can now be taken as 1, 0, 0, 0. Means that is almost like a tautological. But if you're seeing this for the first time, then it's a little different, strange. 0, 0, 0, 1. Yeah. First thing, S direct sum T is equal to Rn.
That part I don't understand. Like,
This is span of 100 and 010 basis.
Yes, this is so Adish. So Rasubru, please explain. Then Rasubru, why is this equal to R3?
S plus T.
S plus T. So S plus T is R3.
So,
that is just because it's a basis. Right?
yeah,
Adish?
basis. And
Yeah.
S
So
intersection T is equals to 0.
yes, I mean, in fact, yes, I've written
but it-
slightly incorrectly. Maybe that was the confusion, because S is not, I shouldn't say S is this, right? I should say that S is the span of this. Yeah, that's well, it's incorrect logically. Yeah, and that can create confusion. The span of this is my S1, S, and the span of this span, just writes, just put a bracket. You can say span, or you can just say. Now it should be clear, and there is no intersection is also clear. Like, that is good enough for us. So this is an example of a projection matrix. Okay. Is this a good example? No, because it's a trivial example. But
Like, how is this a projection matrix?
because it's a projector of S along T, right? If you take this as your S,
yeah,
then it's a projector, right? Because, okay, so if you take any vector, x1, x2, x3, and you put it here, we
yes,
actually,
just projects x1 and x2.
yes, yeah, the output is x1, x2, 0, right?
Yeah.
So it puts it in S, and if you take anything else, it just fixes it, right? I mean, that's how I thought and made the example. So I can say this very fast, but yeah. And if you take anything from like this, then it gives you 0, which just follows logically from earlier thing. So it takes S to 0, and so this is an example. Now, what do we have to prove? What is the question? Let us
So
see.
that big thing is a projection matrix.
Yes. Okay, so no, you have defined that n cross n matrix is said to be a projector. So then what's the definition of projected projection matrix, which is a projector for some S and T?
Yeah.
Right. Yeah, it's a
Now,
little
like below that, it's written that there are some like equivalent statements. Like if A is a projector, then A is idempotent. Now
yeah,
space
that
of A is column space of I minus A.
yes. So if needed, we will refer to those things. Yeah, if needed. This is a very yeah, but here you see it is not n cross n matrix. Okay, and here
But below, where is it written in the
oh
question
no,
paper?
that's a question paper. I don't know if you have the question paper. Oh, you
Yeah,
have the
I
No,
have
I
question.
sent
have
it.
the question paper.
Yeah, no, it's not in the question paper. I think
Yeah.
it's in the notes. I
No,
think,
no.
right? Yeah, it's not. Yeah, it's not in the question paper. At least I cannot see. Yeah, it's not in the question.
Like
Okay.
what?
The properties of projector.
Oh, it's in the book.
Yeah, it's in the book. Yeah, maybe whichever book you are following, you can tell Adish which book is that, or is it book or is it notes?
Rao Bhimshankar.
Rao Bhimshankar. So you can tell him. Yeah, the proper. Okay, let us see. So in this case, it's A is a 3x2 matrix. Okay, so it's a 3x2 matrix. It is very simple, right? So that's a good thing. But still, it may be because the expression is complicated. This A transpose A inverse wow. Show that B is a projection. Okay, so this is a does this become 3x3 or 2x2? 3x3, right? This B is 3x3. Yeah, that way you can check it becomes the 3x3 matrix. And then we want to check that it's a projection matrix. Just a second. Yeah, one can prove this, but it's not that simple anyways. Yeah. Okay. So Adish, do you know how to, sorry, not Adish, Rasubro, do you know how to do this? Can you?
To show B square equals to B.
It is enough to show that?
Yeah.
Oh, I did not. Okay. Okay, so let us see first that, and then we will talk why it is enough to show. So you are now showing B square equal to B.
Yeah.
So let's write it. Maybe that's just a check. Yeah. So let us just check it. This is B, and again we have B.
Into A transpose A inverse.
Yeah. So this is just a check. It's a very interesting thing, right? He's taking any A and he's making a projection matrix out of A. Right? That is
Yeah.
the thing. Okay. So this is B square. So why is it B? Let's check it. this comes, I think. Yeah, this is just identity. Yeah, so it's just a check that b square equal to b. Okay. So maybe what we need to then prove, which I don't know, is that A is a n by n matrix, is a projection matrix, which the properties we described is a projection matrix if and only if A square equal to A. Yeah. So this was one of the definitions which I said initially, which was the best definition, right? It was a crisp definition. This is a long definition, but we want to say that they are the same. So then you tell us, we don't know why they are the same.
So if A is a projector into S along T.
Okay, so you're proving this.
Yeah.
Okay. So A is a projector. Yeah, let's change the language here only. A is a projector of S along T. Okay, and before proving it, can you explain us intuitive, maybe some intuition why A square becomes equal to A before doing the proof, if that's possible?
So A into X that belongs to S.
Okay, A into X belongs to
A
S.
into any X. Yeah.
Why does it belong into S? Maybe it's a silly question, but
So
by
take any
definition.
X n cross 1, yeah, by definition.
By definition, right? It's like S plus T, and what my matrix returns is S. Okay.
Yeah. S.
Right. That's good. And then there is nothing to do because you apply the A again.
Yeah.
And
Then
A
you
of
apply
S is
the
just
again.
S. So
Yeah.
in fact, there is nothing to, in some way, nothing to prove. No.
Yeah.
No. But am I? No. So how does it prove? Oh, because this is S.
So
No. So tell me.
yeah, so this is the thing only. Like
No, but so how? No, we are getting A square of S plus T is equal to S. We want to prove A square equal to A.
A square of S plus T equals to A square S.
Equals to A square. No, so tell me
Like,
again, maybe I made a mess.
so AX belongs to S.
Let's do like that. AX belong to S.
So A into AX should be equals to AX. That's what given in the book, but why I don't know.
Right. Why?
So why is this true? Like I don't know.
Yes, because this is some S. Right? And so it is S plus 0.
Yeah. So
And
A
that will
into
go,
X.
and that will go
Yeah.
to S, which is AX. Okay.
Yeah. Okay. So A square X equals to AX.
For all X, and so A square equal to A.
Yeah. So
That,
for A square equals to.
right. This is one way to see it. Mine is fine, good enough. So we'll keep this. The main thing is actually the other direction.
Yeah.
Yeah, because this is a simple property, but from a nice definition to a, small definition to that. How do you prove that?
So we have to prove that by ourselves, I think, because there are 5 properties given. So they have done like a cyclic thing. 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, and then 5 implies 1.
Oh, okay. Then we'll not prove it. And that's a lot of work. Okay.
Yeah.
Okay. Then we will prove it. I will say maybe the way I understand. So basically, see, if you are given that A square equal to A, and you want to understand S and T. You want to understand what is the collection of vectors along which it projects and what is the collection of vectors that go to 0. That's right. That is what we want to know, right? So yeah. So what is your choice for S and T? Yeah. So if this is the space, if this is for example T and this is S, right? And what is basically happening? You're taking a vector V and you're returning the T component. This is A of V, right? And if you take something in T, then actually that goes to 0. The shadow of that on S is 0. Okay. So the T is going to be the vectors that are getting sent to 0. Right? So we say that, okay, take T to be the kernel, that is the word, but we will just say V such that A of V equals to 0. These projection maps are very, very important. Okay, you can look at, you open any book, linear algebra, any advanced books also, projections will be all over the place, projective modules, projections, or if coming up. You look at the vectors V which go to 0. Okay, this should be one part which should be our T. Okay, and what should be our S? Well, the vectors that don't move, maybe, right? So those should be the thing, the vectors that don't move. Or you can just maybe, not too complicated, then you can just say just the image, right? AV, maybe a different notation, just simple notation, just the image space, right? Because we know that if it was a projector, then that would be the image space. So that's the easier way to say, other than saying that S such that AS equal to S. That will also work, but it's just easier to do this because this will also work. Okay, now we want to just, what do we have to check? First thing, so is the motivation for considering these two subsets clear?
Yeah.
Right. Just a second.
So one you are taking the null space and another you're taking the column space of A.
Yeah, just simple as that. Yeah, just in fact, those are the natural things. Those are the only things which we know actually, right? Null space and the column space, or the image space and the kernel and the image. There is not much that we know, right? Now, what you need to show is that S plus T is equal to all of it. Okay. And you need to show that S intersection T is equal to 0. Okay. So I'm just trying to say that this is the motivated thing. Okay. From what projections are, these are the two things. Okay. Now you see S plus T equal to Rn. Yeah, how do I say this? Because, okay, first you can just check that S intersection T is 0. Right? You would know that from the intuition that it's a projection of it's projecting vectors on something, but you have to check it from the definition also, and it's easy to check, right? So just take something which goes to 0. Just take a V, V such that AV is 0. Okay. Then, so let's say V in T, then you show that it cannot be in the image. Just do all the basic checks. So V is in T, let's assume that V is in T and V is in S. Then you can just do, right? So AV equal to V because V is in S, but AV is also 0 because those kind of things. This is some simple check which you have to do. You should just do it yourself. Okay. But do it. Just use the property.
Why AV equals to V?
Yes, so that's actually maybe wrong. It's not wrong, but it has to be explained. Yeah. So don't use that. Just okay, but okay, let's try to see if AV equal to V. Is that given? No, sorry, AV is not equal to V. Yeah, no. So that's not correct. But yeah, but my point is just check it. It's a very simple check. Just check it. Okay. See, what I'm trying to say is that this fact that S intersection T is 0 will not always happen. It will only happen if this A square equal to A. Okay. Okay. So let's see. So if this you take this is in S. Okay. So you take AV, and if it's also in T, so let's say that AV is in S and AV is also in T. Okay. Then what do we know? Then we know that A of AV is equal to 0 because it is in T. Okay. But this is equal to AV. That is given, right? That's what we wanted to say. But then AV is equal to 0, which means what you started with was 0. So 0 is the only common vector. Okay, that's as simple as that. Okay. So this is just, you have to just use the matrix multiplication and check. Now, why is S plus T equal to Rn? So now again use the intuition. Now, one can say I'll use rank nullity. That will also do. If you know rank nullity, you can use that and some dimension formula. But you don't need that here. Maybe you don't need that. What I'm just saying is, again, look at S, look at T. If you want to more, you can look at the plane, right? T to be a plane. Point is that given any vector V in Rn, how are you going? If I can show you explicitly how to break it into S and T, and that's good enough, right? If I can show you how to break it, then that's also good enough, right? So I take a vector V. How should we break it? Well, you take something in S. You take a shadow of it. You take a vector V, right? So you take the part in S, which means what is S? Right? It is just these are images, right? Image space. So I'll just take the image of V. Okay. What else should I take? I want to break V. Well, I don't have a choice actually. I will have to take this, and then I have to hope that this is in the kernel. But you can check that, right? So the usual suspects work. That is nothing. Yeah. That's it. Because the projection is A, and so I'm taking AV to be the component in S. Other component is determined. And so you don't need rank nullity and you don't need all that for this particular, because the projection is geometric, and so I can actually tell you how to break it. I don't need to use dimension argument to say that, since the dimension adds up to Rn, so on. I don't need that. Okay. That is it. So we have proved this. Problem is done. Right? I mean, from the way we have defined it, problem is done. Right? Because if something is in the image, then it's obviously fixed. If something is in the image, then this is actually fixed. Problem is done. You can check the way we have described everything. It is done. There is nothing to. Yeah. So because given uniqueness, okay, uniqueness also, right? We need to say, right? We need to say uniqueness. But it's unique.
S intersection T equals to 0 implies uniqueness.
This will imply that there is unique, because you cannot write one thing in two different ways. If you write it in two different ways, then you will get an intersection. Right? Then you can do this. This is again in S. If you write like this is in S and this is T, and you write it in another way, then you will have a problem, because you will get this. Then you can write 0 in two different ways. No, but then why is it a problem?
So 0 equals to 0 plus 0, and 0 belongs to S and 0 belongs to T.
That is fine. So
0 equals to 0 plus 0, and so this is not unique. Or say, if it is unique, then 0 equals to V1 minus V dash, and 0 equals to V2 minus V dash, V2 dash.
No, I don't understand. So I know that the intersection is empty.
Yeah. So let's say
it's 0.
intersection is not empty.
No. I have the intersection is empty. I need to show the uniqueness. I need to show that a vector cannot. I need to get a contradiction. See, so I have this, right? This is given.
Yeah.
I need to show that this is a contradiction. I need to show that one vector cannot be written in two different ways. That this is some vector v which I've written in two different ways. Now you need to tell me that there is a contradiction. Right? And I mean, yeah, you're just not able to say it maybe, but you can understand it. This is the W and this is minus W. Okay? Then you see the W is in both S and T. And so W is 0.
Yeah.
And so V1
Yeah.
equal to V1 prime, and hence, I mean, all this is just you have to check, okay, what you expect. Then we are done. Okay. Then this V1 prime will be fixed, or V1 will be fixed. So you take a vector V, V1 will be fixed, and V2 will go to 0 because that's how we have broken up. We have shown you how to break up, and the breakup is unique. That's it. So you don't, okay, I mean, I did it like this, but that's probably better to also do it the okay. Yeah, so there are maybe many other things. So there are other questions, but yeah, we will, as usual, not be able to complete it. We will do it next time. Okay, next week. So this week, maybe Adish, if you get the time, maybe you should, yeah, just start a bit of linear algebra. I mean, you already know a bit, but that book which he's telling.
No, I know nothing.
Huh? No, it's fine. Yeah, so that book that Rasavro is telling, you can start using that. If both of you use the same book, it will be good, right? You people can also
Right.
refer to it. I can refer. Yeah, I've not read that book.
Actually, like I had started with Hoffman. So should I continue with that or should I
Yes,
start
then
with
continue.
Rasavro?
No, then can do with Hoffman only. That's fine. Because I'm not referring to that book's language anyways. I'm not referring to any book's language so far. Use Hoffman. It will be good. We'll bring the different perspectives on the table, right? It will be nice. This is the way. Next time, we maybe both of you.
Like I have also like some problem in like these double sequences in analysis.
But that is analysis, right? So analysis we will have to do next week. Maybe what should we do next week? Okay, let's see.
Next week we can do analysis.
Yes, yeah. Next week, let's do linear algebra only. Okay. So you guys, you read, you continue to read. It's not a problem. So next week, what I'll do is I'll do some problems from Hoffman and Kuntz. Okay.